All right, so let's take a look at the homework from yesterday. So here we wanted to calculate the arc length of an arc intercepted by a 150-degree central angle in a circle that has a radius of 2. All right, so real quick, just to draw it out. Obviously, it's not going to be perfect. All right, so here we have a 150-degree angle. Okay, my radius is 2. And we want to find our arc length, right? So again, our arc length usually we denote with the variable s. Okay, and from yesterday, we know that to calculate the arc length, we need to multiply the radius by the angle. Okay, but again, that angle has to be in radians. So before we can go forward, we do have to do some conversion. So to get the angle in radians, we have 150 degrees. We want to multiply that by pi over 180, right? That's our conversion unit. Right, so we put the 150 in the numerator, 150 pi over 180, and we can divide both of those by 30. 150 divided by 30 gives me 5. The pi is up there. And 180 divided by 30 gives me 6. Right, so 150 degrees is equal to 5 pi over 6 radians. Right, so this is the value that we have to use in our arc length formula. So we're going to take the radius, which is just 2, and we're going to multiply that by 5 pi over 6. Okay, so we can multiply the 2 times 5 to get us 10 pi over 6. But before we do that, it usually helps when we're multiplying with a fraction like this to try to reduce things before we multiply, because sometimes reducing them makes it a little easier for us, right? So this is 2 over 1. So here, I can reduce the 2 over 6, right? They're both divisible by 2. So I cross out this, that becomes 1. I divide 6 by 2, and that leaves me 3. So we have our arc length is 5 pi over 3. Okay, or if you did it and you forgot to reduce, right, when you multiply the 2 times 5 pi over 6, that would get you 10 pi over 6. Oops. All right, but we usually like to have our radians in the fraction part in reduced form. So if you gave me this, you wouldn't be wrong. You just have to take it an extra step and reduce the fraction. Okay, any questions? Oh, and then so some of you also might have multiplied that. Where's my calculator? Right, so we can do 5 pi divided by 3, and that's going to get us about we'll say 5.24. And the units is whatever I told you the units of the radius is, so it's going to be feet. All right, so if you want to be as accurate as possible, all right, there is your answer. Okay, if you gave me either one of these, okay, you'd still be right, but I might just tell you to, make sure it's simplified and all that. Any questions about the homework there? All right. So today we're going to continue with what we left off yesterday in talking about linear and angular speed. So there's a few ways to kind of conceptualize this. I'm going to leave this up here while I kind of explain. So here we have the formulas for linear speed and angular speed. So, the most simple version of this that we kind of consider is we have a particle moving at a constant speed along a circular arc. So we have something, a point in space that moves in a circle. Now, obviously, the examples we talk about, we're not always talking about a point, okay? In the example we're going to look at today, we're going to be talking about the second hand of a clock. Sometimes we talk about a tire or the parts inside a car, right? All the gears and stuff that spin to propel your car. There's a lot of circular motion in life, and it's not always just a particle, right? One of the examples I used yesterday was, the moon orbiting around the Earth, right? Technically there, the moon is a particle. It's a very large particle, but that's where we would consider a particle moving around in a circle. So, oh no, I got rid of it. One second. So one way to kind of look at the linear versus angular speed, okay, is if we have that particle, right, here we have the circle, and the circle's moving. So as this angle increases, okay, that is our angular speed, and this red line that's being left behind, we can consider the linear speed, okay? So this option would actually this representation would more be kind of like a tire, right? So the tire of a car or a bicycle, as it spins, it has that angular rotational speed. But it's kind of like leaving this linear speed behind it, right? As it travels, okay, here is our concept of the linear speed, right? And again, so here's the point of that point A there that we're focused on of our circle, right? This red line is tangent to the circle, right? And that's what we talked about yesterday. The linear speed is a tangent part of our circle. So you have your circle, and then you have the straight line coming from that. Okay, so for linear speed, we need to know the arc length that we are traveling. Right, so to find the linear speed, normal speed, if we're just talking about, basic physics, velocity, that's distance divided by time, right? So since we're traveling in a circle, our distance is going to be the arc length, right? And here I just have a reminder of our arc length formula. So we can actually rewrite the linear speed formula by substituting the s with r theta over time, right? So we have two ways to calculate our linear speed. Let me make that a little clearer. Right, so both of these equations are the same. That's not it. Right? We're just using different values. So sometimes, you're not given all the information, so you can use either one of these. Now, angular speed, well, that relies on the central angle that we move. Okay, so sometimes we're not moving in a full circle. Sometimes it's just, part of the circle. So like with the arc length that we just calculated. Or sometimes we're talking about multiple rotations, right? So remember, one full rotation is 2 pi. So one term that's going to pop up a few times when we're talking about this is something called RPM, right? You might, I don't know, you guys are right at that age where you might start driving. You might see RPMs on your dashboard, right? Talking about that. That's rotations per minute. So that's how many times the little belt inside your car is rotating in 1 minute. Now, for a car, that's a thousand times, right? A couple thousand times, depending on how fast you're going. So your theta, right? One rotation is 2 pi. So if you do 10 rotations, you're doing that 2 pi 10 times, right? So your rotation would be 20 pi. So there we take the amount of rotations we've done and we divide it by the time. Now, before we jump into an example, okay, I want us to notice a few things. Here and here, okay, in both of these, I have theta over time, So I have yet another way to rewrite my linear velocity. I can find the linear velocity by multiplying the angular velocity by the radius. So if you know the angular velocity of something, you can find how fast it's moving in a straight line by multiplying by the radius of the circle. Okay, and one thing that I'm going to show in a second with the example that we do that I also want you to notice is here, this is pretty straightforward, right? It's just how many times we rotate or how much we rotate over time. Here, it's the same thing, but involving the radius. So the linear speed of circular motion depends on how big our radius is. Right? They are proportional, right? So if my radius increases, my linear velocity increases. I could be traveling the same distance in a circle, but if one radius is bigger than the other radius, it's going to be traveling faster. Okay, I have two kind of explanations of this. The first here, what I'd like you to do is focus on the inside circles. Don't worry about the blue outside right now. Focus on this P and the Q. As they rotate, okay, I'd be able to connect a line going through there, right? They are rotating angularly at the same speed, right? Going back, right, they start at the x-axis, and after, I forget what it is, I think 8 seconds. Nope, maybe 10, 9, 10. Right? And at 10 seconds, they end up at the same spot. So for angular, if we're talking about the angular movement, okay, they both traveled the same distance in 10 seconds. Right? They did one rotation in 10 seconds, one rotation in 10 seconds for both P and Q. Right? So their angular speed is the same. But look at the actual points themselves. Q has a larger radius, right? Q is further away from the center. If you just kind of focused on what was going on with the points, Q has more of a distance to cover because that circumference is larger. So the linear speed of Q is faster than the linear speed of P, even though their angular speed is the same. Okay, a real life example would be anytime that you use a fly swatter. All right, flies are pretty fast. They have a good reaction time. If you just swing your hand down, right, like if I looked at the tip of my finger as the particle, the point, right, to go from here to here, say I do it in a second, right, that's kind of fast. I can move it faster, but it's not very fast. The fly has plenty of time to, evade my attack. If I extend my arm by, maybe a foot with a fly swatter, this point that's all the way up here, as I fall, that has to move faster than my hand, right? It has to cover more area. the motion that my hand is doing is maybe 90 degrees, right? So the angular distance is the same. But the linear distance, this point that would be above my hand, has to move faster because it's moving a greater distance in the same amount of time. All right, so let's look at this concept with some actual numbers. No, I don't want to exit. All right, so we're going to look at a clock. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock. All right, so let's think about this. So we have a clock, we have a second hand. What's nice about this example is we already kind of know the angular speed, right? A clock, most clocks are, pretty accurate. The second hand travels around, it makes one full rotation every 60 seconds, right? That's what a clock is. So my angular speed, no matter what length my second hand is, it could be 10.2, it could be half of that. My angular speed is going to be the same, right? One rotation every 60 seconds or one rotation every minute. But the linear speed depends on how large that second hand is. So for linear speed, we need a few things. We can do the arc length. And then obviously time is simple because it's 60 seconds or 1 minute. So the arc length that we're traveling, okay, if I'm making one full rotation, then the central angle that I have is going to be 2 pi, right? One full rotation is 2 pi. So for S, right, going back to our S formula, the arc length is going to be the rotation times the radius. So we're going to have 2 pi times my radius, 10.2. So here, we're going to keep it simple. I'm going to keep the pi there. So I'm just going to do 2 times 10.2. So that's going to get us 20.4 pi. Okay, and the radius is in centimeters, so the arc length is in centimeters, right? So the tip of this clock in 1 minute travels 20.4 pi centimeters, okay? So you can lay that out flat, right? Because we're talking about the linear speed. Our time, we said, is 1 minute or 60 seconds, right? So sometimes you just got to be careful. They may ask for the linear speed in specific units. So there you just got to, pay attention to what they ask you. They might say, what is the speed in centimeters per minute? Or they might say, what is the speed in centimeters per second, right? So then you would have to determine which one to use. We're going to use seconds, right? So our velocity is going to be the arc length that we traveled over time. Right, so we're just going to plug in 20.4 pi over 60, and that we would use the calculator for. Right, so 20.4 pi, 20.4 pi divided by 60. So we have 1.07, we'll say. Right, so that velocity is, now we just got to be careful with our units. Our units here was centimeters, and we used seconds. So we're going to have 1.07 centimeters per second. All right, so if you laid this out flat, or if we looked at it like we saw that example before, excuse me, where this, if you think of this as the second hand, right, and instead of watching the second hand go around, you kind of follow it so the second hand is always pointing down, then your clock is going to be rolling very slowly. Well, not very slowly, but pretty slowly at almost 1 centimeter every second. Right, so if we had a shorter second hand, right, if I maybe took half of that, I would be cutting this in half, which would cut this in half. Right, so if I had a radius of 5, everything else would be the same, and I would have my arc length being 10 pi, and then my linear speed would be 10 pi over 60, and we'd only have about 0.5 centimeters per second. All right, let me just... Yeah, 5.2 centimeters per second. So there, mathematically, we can see the longer the radius, the faster the linear speed is. All right, any questions there? We kind of covered a lot.